We're going to discuss the idea of derivatives at a point and equations of tangent lines. So as a little recall, a general derivative of a function y equals f of x is denoted by either y prime, f prime, using the prime notation, or the operator notation of dy over dx. And that derivative ultimately represents the slope of the tangent line at any point on our curve. So this does represent the slope of our tangent line at any point. So as we're finding our derivatives, we've been getting equations for all of these. So as we're finding f prime of x or dy over dx, we've been getting equations. Now, a derivative at a point is specific to that point that we're substituting the value in at. So formally, using a general derivative, we can find a derivative at any point a comma f of a by substituting that x value of a into f prime of x to get f prime of a. Now, what doesn't change is the underlying idea of a derivative. This is still representing the slope, but the difference now is this is the slope at that specific point a comma f of a, whereas our general derivative was the slope at any point. For the slope at a comma f of a, this would end up being a number because we're getting the slope at one specific instance in time on that graph. Now, an important thing to note is we must always find a general derivative, our f prime of x, first before we can find our specific derivative. Notationally, if we've got the prime notation, it's pretty straightforward using kind of function notation that we're used to from prior classes. We would find f prime of a now, substituting in whatever that number a may be. But if we have this operator notation of dy over dx, we use a vertical line to represent evaluated at, and then a subscript x equals whatever that a value is in the subscript to mean I want to take my derivative, the dy over dx, and I want to evaluate it at whatever that x value may be. Let's look at a couple examples. So in our first example here, we're asked to find f prime of 4 for the function f of x being 7x minus 25 entire function cubed. The first thing that we need is we must get, again, that general derivative. So I need to find f prime of x first before I can find f prime of 4. So to find f prime of x here, think about what rules we may need to use. So in this problem, we're going to need to use the chain rule because our outermost function here would be a 3. Then our inside function is 7x minus 25. And then we're also going to need a power rule in it. So to take the derivative of something to the third power, that 3 would come down. We'd keep the inside the same, so 7x minus 25 stays the same. To now, the second power by subtracting 1, and then times, to finish off the chain rule, we need to take the derivative of the inside, and the derivative of 7x minus 25 would give us 7. Now from here, I'm going to do a little bit of simplification. The 3 times the 7 could get multiplied, giving us 21 times 7x minus 25 all to the second. And that would be our first derivative, or our f prime of x. Now we're asked to find f prime of 4. Now that we have an equation for f prime of x, I can now substitute in 4 in place of any and all of the x's. So I'm going to end up with f prime of 4 now equaling 21 times 7 times 4, since we're substituting in 4 for the x, minus 25 all to the second power. Now to simplify this down, using order of operations, I'd still have the 21 on the outside. 7 times 4 would give us 28, minus the 25, all to the second. Simplifying that down, we'll get 3 squared. 3 squared is going to give us 9, and then 21 times 9 would give us 189. And 189 there would be our final answer for finding f prime of 4. I do want to point out a couple important things with the notation here. Notice how I've specifically labeled my first line f prime of x because that's giving me my general derivative, or this equation involving x's. And then on my next line, I didn't just put equals to the previous line, but I've now relabeled this as f prime of 4 because we are now specifically finding the derivative at 4, and then we simplified that all the way down. This idea could be used to find f prime of maybe 2, f prime of negative 3, even f prime of 0. We can ultimately find f prime of any number once we have our general derivative first of finding that f prime of x. Okay, let's look at another example. So here we have the function y equals 3x squared minus 8x plus 4 in parentheses times x to the fifth plus 2x minus 3. and we're asked to find the derivative evaluated at x equals 0. So in our second example here, we're seeing that operator notation. It's the same idea though. I want to find my first derivative, and then I want to evaluate it this time at x equals 0. So in order to do this, I first need a general derivative. So I first need to find dy over dx. What rule or rules are we going to need to use in order to find the derivative of this function? So in this case, we're going to need a power rule again because we are dealing with polynomials, and we're also going to need a product rule since we have this quadratic times this 5th degree polynomial. Why don't you guys find the general derivative on your own first? Okay, using the product rule, let's check that derivative. So the product rule says I take the derivative of one function at a time while keeping the other function the same. So I'm going to start by taking the derivative of the quadratic, which would give us 6x minus 8, times, I'm now going to keep this x to the 5th function all the same, plus I now need to reverse which one I took the derivative of. So now I'm going to keep the first function the same, so 3x squared minus 8x plus 4, times I now get to differentiate the second function, which would give us 5x to the 4th plus 2. And that would represent our general derivative at any value x. Now in this problem, we want to find the derivative specifically evaluated at, so again that vertical bar means evaluated at, and in this case we're evaluating at x equals 0. So just like up above in example 1, I want to substitute in whatever that numerical value is for x into all the x's. So this time I'm going to substitute 0 in for x. Now the nice thing about when x is 0, a lot of this is going to actually zero out. So when we substitute in 0 into the 6x minus 8, that's just going to leave us with a negative 8, since 0 times anything would be 0. And then for the x to the 5th function, the x to the 5th will zero out, and so will 2 times x. So that will just leave us with minus 3. Plus, in our third function here, when the first two terms, the 3x squared minus 8x will zero out, and we're just going to be left with 4. And then in our last function here, the 5x to the 4th would go to 0 when we sub in 0, and we'd just be left with the positive 2. We can simplify this down a little bit further. Negative 8 times negative 3 would give us positive 24. 4 times 2 would give us 8, and their sum together would be 32. So here, our derivative evaluated at x equals 0 ends up being 32. Again, I want to stress the notation here with my first line being the general derivative, and then my second line being the specific derivative evaluated at x equals 0 overall. And we can see how we're seeing all of our derivative rules that we've seen before with the chain rule and the power rule in example 1, and then the product and the power rule in example 2. Okay, let's look at a third example. So here we're given the function g of x, which is 12 times the square root of x, and we're actually asked to find g double prime of 4. So g double prime is representing our second derivative. So in order to get to g double prime of 4, I'll first need our general second derivative, but we know from our last section that to get our second derivative, we ultimately need our first derivative. So we're going to have a couple more steps in this one. The first thing I actually want to do is rewrite this original function so that I have x to a power. We know that the square root is the same thing as the 1/2 power, so we can rewrite that as 12x to the 1/2. Let's start by finding our first derivative. I'm going to let you guys find the first derivative on your own, and then we'll check it together. So here, using the power rule, the 1/2 would come down. 12 times 1/2 would give us 6. We'd get x to then the negative 1/2 by subtracting off 1 from that exponent. Now, if we were stopping at the first derivative, we would want to rewrite this without a negative exponent, but ultimately, we're just trying to use the first derivative to get to the second derivative, so I'm going to keep going. Why don't you guys find our second derivative, and then we'll check it together. So with our second derivative, still using the power rule, when we bring down the negative 1/2, 6 times negative 1/2 gives us negative 3. Then we'll get x to the negative 3/2 by subtracting off 1. Now, we're interested in finding in this question g double prime of 4, so it would be worth our while to go ahead and rewrite this without negative exponents. So the negative 3 would stay in the numerator, and then x to the negative 3/2 can flip down to the denominator and become x to the positive 3/2. And this will help us when we have to simplify in a second. Now that we have our second derivative, I can now evaluate the second derivative specifically at 4, and that means I'm going to sub in 4 for all of my x's. So we're getting negative 3 over 4 to the 3/2 power. Now to simplify this, we've got to think about what the 3/2 power means. So in this case, the 3 is representing the exponent, or well, the whole thing's the exponent, but the 3 is representing the power. So I want to cube something, and then the 2 in the denominator is ultimately representing our square root. So I could rewrite this one of two ways. I could do the square root of 4, whole thing cubed, or I could also do 4 cubed and then square root that whole thing. Personally, for me, I prefer to do the square root first, since this will make our numbers smaller. I'm going to get negative 3 over 2 cubed, and then from there, 2 cubed would give us 8. So we're ultimately getting g double prime of 4 then to be equal to negative 3 over 8. So we can see how all those kind of algebra things that we've been talking about building up this whole year and in prior classes are coming back when we need to simplify some of these derivatives at points. Now that we know what a derivative at a point is, we can expand on this idea and think about how we could form an equation of the tangent line at this specific value. So again, to recap, the derivative at this point is giving us the slope of the tangent line. And so if I want to get an equation of the tangent line, I'm ultimately going to need that information plus the point that we're finding this at on the original graph. So to recall a few things, if I want an equation of a line, this would require us to have a point and to have a slope. Now our point is going to be the coordinate pair a comma f of a that we're finding this tangent line at, and the slope is ultimately our derivative, or f prime of a specifically, because I want the slope at that specific instance in time. Now with a point and a slope, we have a lot of different equations of lines from Algebra 1, but the easiest one to use would be point-slope form. And to recall that, that would be y minus y1 equals m, where m is our slope, times x minus x1. And again, x1 and y1, for a little algebra refresher here, is just the point that we're writing this equation at. So that would really be our a comma our f of a. And if we had a multiple choice question and we needed to get our answer into slope-intercept, once I put it in point-slope form, then we could easily kind of distribute the slope and isolate the y to get it into slope-intercept form. But since we have to get a slope from our derivative and a point that we're given, then point-slope form would be the easiest way to get that equation, and then we can manipulate from there if need be. Okay, let's look at our first example. So in example 4 here, it says write the equation of the tangent line 2f of x, which is x to the 4th minus 7x squared plus 8 at x equals negative 1. So for all of these problems, we're going to need two things, our point and our slope. So I'm going to have us start by finding our point. Now we're given our x value. So we know that this is happening at x equals negative 1, and we have to be given kind of a starting point. So that means ultimately our point is going to be negative 1 for our x value, comma, I need to know what the corresponding y value would be, which would be our function evaluated at negative 1. So I'm going to start by finding f of negative 1. I would do that by subbing in negative 1 for all the x's. So we get negative 1 to the 4th minus 7 times negative 1 squared plus 8. Simplifying this down, negative 1 to the 4th is positive 1. Negative 1 squared is also positive 1, but we're multiplying to the negative 7. And then we still have the plus 8. That would simplify down to give us 2, which ultimately means the point that we're working with for this example would be negative 1, comma positive 2. And we can already start to think about filling in that point-slope form now that we have that x and that y value. But let's find our slope so that we can get the whole equation at once. So our slope again is going to come from our derivative at this x value, so f prime at negative 1. To find that, we ultimately need a general derivative first. So I'm going to start by finding f prime of x. Why don't you guys use the power rule and find our derivative on your own first? So to check that, using the power rule, derivative of x to the 4th would give us 4x to the 3rd. Derivative of 7x squared would give us negative 14x to the 1st, and then the 8 would drop to be 0. There's our general derivative. To get our specific derivative at negative 1, we're going to sub in negative 1 for all these x's, and then simplify down. Oops, that's going to be a negative 1, not an x. So we end up with negative 4, because negative 1 cubed would be negative 1, times 4 gives us negative 4, and then plus 14 from the double negative being multiplied, which ultimately would give us positive 10. Now that we have both our point and our slope, we can get that final point slope form equation of our line, which would be y minus our y1 value is going to be 2. That's our f of negative 1 that we found over here, equals our slope, which is 10, times x minus our x1 value would be x minus negative 1. So we could simplify that to be x plus 1. And that right there would be our equation of our tangent line for this function at x equals negative 1. All right, let's look at another tangent line example. So this time, we're asked to find the equation of the tangent line to y equals x squared minus 1 whole thing cubed at x equals 2. Let's start by finding our point. So we already have our x value of 2. How could we find the corresponding y value? Now the y value, when x equals 2, would be coming from subbing in 2 into the original function. So I could use y of 2 to represent that. To do that, we're going to change and sub in all the x's to be 2's. So I'm going to get 2 squared minus 1, entire thing cubed. That would give us 4 minus 1, which would be 3 cubed. Ultimately will end us with 27. So for this problem, our point's going to be 2, 27 for our y value. So we have half of what we need already. The next piece we're missing is our slope, which is coming from our derivative at 2. So that would be, I'm going to use the operator notation just to see some variety. So that would be our derivative, dy over dx, evaluated at x equals 2 would be our slope. Now to find that, though, we need a general derivative first. So I've got to start by finding dy over dx in general. Why don't you guys find our general derivative in example 5, and then we'll check it together. So for this one, we're going to need the chain rule. The 3 is the outermost function. So that comes down, we keep the inside the same, all to now the second power, times the derivative of the inside there would give us 2x. And just to clean this up a little bit, we can multiply the 3 and the 2 to get 6x, x squared minus 1, whole thing squared. And if you don't simplify the general derivative down first, that's okay, because eventually, once we sub in the next step, we're going to have to simplify and multiply stuff together anyway. So now if we want to sub in and find the specific derivative at x equals 2, we're going to get 6 times 2 times the quantity 2 squared minus 1, whole thing squared. So that would give us 12 from the 6 times 2. On the inside here, we're going to end up with 3 again, but it will be squared. 3 squared would give us 9, and then 12 times 9 would give us 108. Just save us some space. Now that we have a point and a slope, we can go ahead and write this in point slope form. So we're going to get y minus our y1 value is coming from our y of 2, which we found to be 27, equals our slope is our derivative at x equals 2, so that would be 108, times x minus our x1 value, which is 2. And that would be our equation of our tangent line. Again, like I mentioned up above, if we had to get this into slope-intercept form, we could go ahead and distribute the 108 and then add the 27 over and combine some like terms, and then we'd be in slope-intercept form. But if it's a free response problem or if the multiple choice is in point-slope form, we'd be done at this step. Okay, let's look at one more example. So here in example 6, this is a little bit different. I'm not actually given an equation. Instead, I'm given a couple pieces of information. So I'm told that h of 9 is equal to negative 4, and that h prime of 9 is equal to 5. And we want to find the equation of the tangent line to h of x at x equals 9. So we're still trying to find the two things that we've been doing in the prior two examples, where I need a point and I need a slope in order to get my equation of my tangent line. Well, the point is going to come from the x value of 9, which we were told to find the tangent line at, comma, the corresponding y value, which comes from whatever h of 9 is equal to. Now, unlike our prior two examples, we're actually directly given this. So although I don't know what h of x equals, I am told that h of 9 is negative 4, which means our point then is 9, negative 4. Now that we have that, the next piece we're going to need is our slope. Well, our slope of our tangent line comes from our derivative at that x value. Our function here is h, which ultimately means I want h prime, that derivative, at 9 in this instance. Although, again, we don't have an equation for h of x, so I can't find a general derivative, I am told that h prime of 9 is equal to 5, so I actually have my slope already. Putting both of those pieces of information together, using point slope form, I'd get y minus our y1 value, which would be -4. So I could write that as y plus 4 then, from the double negative, equals our slope of 5 times x minus our x1 value of 9. And that right there would be our equation of our tangent line for h of x at x equals 9. So although example 6 here is a little bit different, it's actually kind of a nicer problem where as long as we're understanding where the pieces are coming from to create an equation of a tangent line, there's not much computation I need to do. I instead need to conceptually understand how to connect these dots of the point being the original x value that we're given and then the function at that x value, and the slope being the derivative at that x value that we're given. From there, using point slope form, we can put it all together and we get our full equation of our tangent line.